Welcome to the second module of our video. We're going to talk about the entire process flow from start to finish. So first, print preparation, slicing, printing, and debinding and sintering. Let's talk about printer requirements. What kind of printer do I need? What can you use? Kind of things. One thing that's important is your printer is suitable for this process. So this material has been designed to work on as many FFF platforms as possible, and we like to think it's analogous to one of our ABS filaments. So you're going to want an extruder that can go up to 240, 250, a heated bed of about 90 to 100, and enclosure is good because you want to minimize any airflow, and you definitely want to turn off part cooling because that'll force delamination and things like that. Now, this will work for many hobby machines, many prosumer machines, up to industrial machines, but we want to make sure the minimum requirements are met. And enclosing the part is very important. Again, thinking more like an ABS methodology. Now we're going to talk about the print preparation and going from basically art to part. So you'll start out with a CAD or computer-aided design model that can be made in any design software. That model is then translated into an STL or sometimes a 3MF, and that's the input for a slicer. The slicer process basically converts that model into G-code or printer instructions that it can then create the model layer by layer, or slices. That's why we call it a slicer. And as those layers get built up, then it becomes a 3D model. So in general, you take your CAD model, convert it into an STL, then in the slicer you prepare it for printing. That creates G-code, which is then sent to the printer as instructions to make your part. So let's talk about some of those slicer programs. You can use many different types. It's kind of personal choice or machine choice. There's many open source systems like Prusa or Slice R or even Cura, and other ones like Simplify 3D, IdeaMaker from Race 3D. We have tested all of these systems and found ways and parameters, and that's something you can request from us. We can give you profiles, we can give you hints, tips and tricks, and of course there's a very large library of tips and tricks online and at these distributors and producers that can get you even closer to where you need to be, quickly and simply. Okay, now let's talk about printing parameters during the slicing process. One important fundamental is the nozzle size, typically around 0.4 to 0.6, but we've tested between 0.25 and 0.8. Extrusion multiplier. It should be calibrated using a single wall calibration method in order to ensure the right size is being printed for your G-code. Retraction distances between 1.5 and 5 millimeters in direct or Bowden style have been chosen most effective. Retraction speeds of around 45 millimeters per second. Layer height is going to depend on the required resolution or part size and nozzle size, but typically 0.1 to 0.25 millimeters. Outline overlap percentage of typically 20 to 35%, and maybe even higher to ensure that outer walls are stuck to the infill. Nozzle temperatures around 235 to 250 are recommended, with a bed temperature between 90 and 120 degrees Celsius. Cooling is a very important point. Make sure to have cooling turned off because this can increase warpage and delamination. Print speeds, typically around 35 millimeters per second, have proven the best mix between quality and print time. And shrinkage, which will go in further in later sections, our starting parameters for shrinkage are around 16% X and Y and 20% in Z. Print orientation. Most parts will have a suggested direction, but we can also provide simulations for this. In general, you want to reduce your overhangs and you want to reduce the use of supports because, like other materials, the final part, those supports will be made out of metal and will require cutting or removal. Now that you have G-code prepared from your slicing software, we're going to start about the printing process. Now, one important thing is your first layer. Everything is built on that first layer, so it's important and critical that you have both good filling and good attachment. So making sure that the extrusion multiplier is tuned in such a way that you're getting enough purchase of the material to the build surface. Sometimes when your extrusion is tuned high enough to produce dense parts, you will get a certain amount of buildup at the nozzle surface, and that's typically normal for us. We want to have enough material that's ensuring full density. At the same time, sometimes people will look at it and think it's kind of strange. Now, of course, like any good thing, too much is a problem. Those parts can crumble off the nozzle and block other things, so it's something to be balanced. You want to be printing as dense as possible, and therefore you might have a little bit of buildup to deal with. So usually using a brass brush or something like that to make sure the nozzle is clean each time you start printing, it'll really help you out. One important part is the bed adhesion, and there's different settings you can do to help the part stick. One, of course, you're always going to probably want to have a little bit of a brim or to flush the nozzle and make sure that you have proper flow. Now, if a bigger part or parts that might have warpage or other problems like that, definitely a couple of brim layers or skirt layers can help. And don't be afraid to use a raft. If you need to have it, use the raft to get it to print. The good thing about our material is it can be easily cleaned off. So you can print with a raft to ensure proper adhesion to the build print. And then after you're done printing, you can take the green part out and remove that raft and send it on for debinding and sintering. Before printing, it's advisable to add an adhesive. Now you've printed your part, and you can see you basically want to go from our green part down to our metal part. And as you can see, there's that shrinkage we talked about 20% in Z and about 16% X and Y. So in order to get 316L to be fully metal material, when you're done with it, you have to remove the binder used, the organic compounds we use to bind the metal parts together. And that's done in a thermochemical process called catalytic debinding. Now, catalytic debinding, put simply, is just removing the non-metal parts and then, in the sintering process, combining the metal parts into one solid part. Now your part's been debound, it's now what's called a brown part, and it's ready for sintering. Put simply, sintering is just combining the metal particles into a solid part using temperatures and pressures. In this case, it's around 1400 Celsius for 316L. Now, this is also where you're going to see that shrinkage, where you're seeing 20% in Z and 16 in X and Y. That is oriented with the print method. So the Z level, with the layers, that's the direction that's going to shrink the most. So it's important to understand which way the part is going to be set up and how to properly scale it. One thing we'd like to add to it is, unlike other metal additive processes, we have the ability to treat and form and adjust the surface and features of our part in the green state. Because it is a polymer-based process, you can sand it and grind it, sandblast it and polish it, kind of get the part closer to the surface quality you want to have before it goes into sintering, right? And at the same time, of course, it's 316L stainless steel. It can be polished, it can be welded, other things. And like to say, the interesting part is that it's additive metal. The boring part is it's just metal. You know what to do. Spray paint it, sandblast it, and treat it to whatever specification you need your final part to have. And for more details, you can see into the design guidelines section of this video.